Right, the last topic that we're going to talk about here in quantitative reasoning is going to be exponential growth and decay curves. We're just going to talk about them conceptually, that it's one of the nonlinear models that we run into a lot in nature. I'm going to show you what one looks like here. So y equals, and I'm just going to use the e to the x function. Don't worry about what e is. It's just one of the bases that we see a lot in nature. And so it's kind of hard to see, but it's getting closer and closer and closer to this line y equals 0, and it rises as it goes to the right. We could also have exponential decay, where I would have a negative exponent up here. Let me get back there and make this a negative x here. And it would fall to the right like that. But the general shape of an exponential growth function, since we're growing, is going to be a rising curve. That was the first one that I drew. Sometimes people will call it a hockey stick graph. A exponential function is something where the rate of change, the slope of the function, is proportional to the amount of material that's present, the quantity. We're going to use the function name q of t here to represent a quantity that we have at any point in time. So that is, the more that I have of the substance, the faster the rate of change. So when I have not much of something, the rate of change is small. When I have a lot of the thing, the rate of change is big. So that's what they mean when they're talking about the relative amount. They're talking about a percent change. And that is true, that the percent change is the is what determines the exponential rate of growth here. So this is true. And it's written in the form, well, we'll see the equation down here in just a second, but it's written in this form: original quantity times 1 plus this rate of change, this percent growth or percent decay per unit of time, like per year or per day or something like that. True or false? Exponential functions are useful for modeling lottery numbers. That's false. The whole idea of a lottery is that it's not easy to model, it's random. So true or false? After 80 years, a population growing at a rate of 8% per year will have grown by twice as many people as a population growing at a rate of 4% per year. No, that's not true. Let's go ahead and show those models though. So let's say that both communities start off with 100 people. And they're getting multiplied by 1 point, this one is 1.08 to the t, and this one is 100 times 1.04 to the t. And I'm going to go down here to, how many years did they say? 80 years. Look at the table. And I'm going to see that no, in no way is 2,305 half of 47,195. That's false, right? Because I'm getting increase on the increase on the increase at 8%. It's compounding. So this goes back to the idea of when we did financial math and we talked about compound interest and how you earned interest on the interest. That was an exponential growth model that we used back then. We just didn't talk about it that way, but it was. If you remember, it was A equals P times 1 plus R over N to the NT like that. And if we were only talking about 1 year, then, or one payment a year, then it was this. Look at how close that looks to this, where P is A naught, R is the rate of growth, the APR, and T is the number of years. It's exactly the same model. Okay. The population of a town with an initial population of 62,828 grows at a rate of 2.4% per year. Create an exponential function for that model. So we've got 62,828 times 1 plus the rate of growth. So 102.4% raised to the T. You see that down here. We're going to call this, I would call it P of T because it's population, but they're using it in the form of Q or Q of T equals. So I'm going to do what they told me to do there, but I use letters usually that represent what I'm trying to find. And if it's population, I use P. If it's amount, I use A, and so on. The population of a town with an initial population grows at a rate of 2.7% per year. Create a table now showing this. So we're going to have to stick this into our calculator to make the table. So 57,655 times 1.027 raised to the X. And I want my table to go by ones and to start at 0. And we just want the table for the first 5 years. So from 0 to 5. And let's check our answers that we have here with the key. So 57,655, check. 59,212, check. 68,10, check. 62,452, check. 64,138, check. And 65,870, check. Okay. So now they want us to graph an exponential function. Again, we're going to use the calculator for this. So original population is going to be 56,112, and it's going to grow at a rate of 3.3% per year. So that's 1.033. We're going to raise that to the X. And I'm going to zoom 6. I'm probably not going to see anything at first. So I'm going to have to zoom out here. I'm going to hit zoom 0 to make the calculator estimate what a good window would look like for this. And it's showing me that rising curve. I'm going to zoom out a little bit more so that you can see the shape of it a little better. Okay, you see that? And so that would be my graph, and I could give my teacher my window, or I would put that on my graph paper there to make sure that I had the scale indicated for the instructor when I made my graph. Because these numbers are so big, though, I'm not going to be able to use tick marks that are equal to 1 because we're talking about things that are tens of thousands here. So there's the scale that the teacher used. Let me get the window the same way here. And we're going to start. Okay, let's actually show you how she did this. So clear, enter, and she just wanted data points for 0, 1, 2, 3, 4, and 5. And then she came here and used this model of 56, 112 times 1.033 raised to the, and now instead of X, I'm going to use the number that's in my first list. That's only going to give me these data points. I'm going to get rid of my Y equals because I don't want that line there. I'm going to go into stat plot, and then I'm just going to graph a scatter plot here, turn my plots on, and I'm going to zoom 9, that's zoom statistics, and I'm going to make my graph match hers now. So window, my X min is going to be 0. My X max is going to be 5. I'm going to go by ones. My Y min is going to be 3,000. My Y max is going to be, 30,000. My Y max is going to be 90,000. And my scale is going to be by 10,000s. And there's the data points that we got. Okay. Population of a town with an initial population of 72,526 is decreasing at a rate of 3.5% per year. So 1 minus 3.5% is a rate of we're keeping 96.5% of the population each time. So our equation here is 56,112 times 0.965 raised t. I'm sorry, that was this one down here. Decreasing, so this should have been a minus here, but this is Q equals 72526 times 0.965 to the t. Population of a town with an initial population of 69,064 is decreasing at a rate of 2.8%. So we're keeping 97.2% of 69,064. And we want to create a table showing the first 5 years. Turn those plots off. 69,064 times 0.972. Gonna start at 0, that's good. Let's look at number 9 here. 69,064, check. 67,130, check. 65,251, check. 63,424, check. 61,648, check. 59,922, check. I think this is, yep, this is the last problem here. Population of town with an initial population of 52,576 is decreasing at a rate of 4%. So we are keeping 96%. Make a graph of that. come back y equals, we got 52,576 times 0.96 to the x. I'm going to zoom 0. I want to see a little bit more of that exponential shape, so I'm going to zoom out a little bit. And if I did not zoom out here, I might assume when I was zoomed in so close that it was a linear graph, right? It looks very linear when I zoom in close, but as I zoom out more, I can see that it's this falling curve here. So there's my model for Q of t. It's a function, so I can write it in function notation like that. And so again, we only got data points shown there, but the curve is going to connect the dots for us as a function. All right, that's it. Hope you enjoyed this video series, and good luck in your next course, which is probably statistics after this.